So, welcome to the 10th lecture in the Introduction to Lattice Boltzmann methods, winter semester 25-26. And today we finally get to the interesting things with the Cumulant method. So, why we need yet another model after we learned about the MRT method? So we have identified some problems with using multiple relaxation times. I first have to check the microphone. Yes, I think I'm on. So there were a few. So we have observed that we have dependence of moments. So the moments, we like the moments to be independent variables, but we have seen that they actually depend on each other. And we've also seen a way to overcome this, but this was a little bit strange. And we also like to understand this better. So we could overcome this only with a weighted orthogonality. And the question, when we have, so, I mean, we looked only at two different, actually, one moment, yeah, and see that there is this problem, and that when we do something specific, we can make it orthogonal to one other moment. Okay, yeah. The question, I mean, one question is whether this is general, but also the other question is where do we get the weight from? Or the weights from? So this is one problem, and another problem that we did not discuss in this detail, but that's also obviously a problem, is that the moments are defined in an Eulerian frame. So why Eulerian frame? Because the velocities, so we integrate over velocity, yeah? And what is velocity? So we have to define velocity with respect to something. And if we change our frame of reference, then our moments will look differently. So that's a problem of MRT, because we have moments that we kind of define in an arbitrary frame of reference. I mean, it's not completely arbitrary. It's the frame in which we have in which our lattice velocities are symmetric. Yeah, so we like this, but from a physical point of view, of course, this is arbitrary. Yeah. So, well, the question, if we define something in an Eulerian frame, of course, that we should ask is, can such a thing be Galilean invariant? So in Lattice Boltzmann, in numerics in principle, but in Lattice Boltzmann in particular, we care a lot about Galilean invariance. I think we have not discussed this to much extent here, no. So what, not at all, right? So what is Galilean invariance?
In every IS frame, reference frame.
IS, inertia. In every inertia reference frame, yeah.
The quantities are the same.
No, the physical laws are the same. I mean, the velocity would be different from one to another, yeah, but the physical laws, so the equations that you have to solve, they should be the same. And this is, of course, only true for inertia frame. For example, here on Earth, we are not in an inertia frame because our Earth turns, so we experience Coriolis force and centrifugal force. For example, centrifugal force is when I guess you guys come from a place that is further south, so you will have less gravity on you, yeah, like this going to India or not to going to India makes a difference for me for like one packet of chocolate, yeah, 100 grams. Welcome. So, I mean, this last thing with the Eulerian frame could be solved by another means, namely, always the same as this. We could use central moments instead. In order to be sure that we are Galilean invariant. So what are central moments? Yeah, we have to so central moments are moments taken in a Lagrangian frame. And this is the material frame. So let's compare this. So what we call raw moments are the ones that we have in the Eulerian frame, raw moments. And now we have defined them many times. I'll define them again. MABC is equal to the sum over all the indices I, J, and K. I by the power of A, J by the power of B, and K by the power of C into Fij, So this is what we use all the time, right? So these are the raw moments. By the way, for just a notice, because I discovered that some people who were in my lecture did this wrong later. If you do the asymptotic analysis as we did in lecture 8, we need to use raw moments, yeah, because these derivatives, they are only true with respect to a specific frame of reference. So we could choose a different frame of reference, but we have to choose a frame of reference. So when we talk about central moments, which are in the material frame, we have the problem that in a different point of the material, they have a different velocity, so we define the moments differently. Yeah? So this is why in the analysis, it's important to use raw moments and not central moments. Because first of all, it looks easier to do it in central moments, but the result is wrong. So central moments. So I write central moments with K. KABC is equal to the sum I, J, and K. So now what we are doing is we take the moments with respect to the frame of reference that is moving with the fluid. Yeah. So then we have not the velocity I in the x direction, but we have the velocity I minus the macroscopic velocity u, and that to the power of a, this j minus the macroscopic velocity v, this to the power of b, and k minus w, this to the power of c, and that's an fijk. So now the question, what is u, v, and w? U, v, and w are defined such that the moments are central. So central mean they are symmetric, or the distribution is symmetric. And if the distribution is symmetric, then the first moments are zero. Yeah. So basically, u, v, and w are defined from this setting it to zero, yeah, and then solving for u. And this is the velocity, this definition of velocity. So there is a way to translate between the raw moments and the central moments, or moments in a different frame of reference. This is the binomial transform between frames of reference. So this looks like this. We can write K, A, B, C. So this is the central moment as a triple sum over alpha equal to 0 to A. So A is the first index here. And beta equal to 0 to B. And gamma equal to 0 to C. So A, B, C, these are the indices. Now we have the binomial A over alpha. If you're not familiar, I will define this shortly. B over beta and C over gamma into -1 to the power of A minus alpha plus B minus beta plus C minus gamma. So unfortunately, this is a little long. Yeah, so I have to continue in the next line. There's a multiplication of this with what is now following. We have M alpha, so these are the raw moments, M alpha beta gamma. Yeah, and now what you immediately see is that the highest order of these things is ABC. Yeah, so there's nothing beyond that, but there's something below that. Yeah, MABC, and this goes into M100. So this is the first moment divided by M000. So this is the velocity. Yeah, so it's because it's the momentum divided by the mass. Yeah, and this into R minus alpha by the power of R minus alpha, M01. So this is the velocity in y direction, B minus beta, and M001 divided by M000, and this to the power of C minus gamma. So, okay, what we observe here is that we have this central moment as a function of raw moments up to the same order. Yeah, and this also is a polynomial in the velocity. However, it is not a polynomial in the raw moment. So you see, each raw moment comes only once. It's a polynomial in the velocity, but not in any other moments. Yeah. This is, by the way, when we later come to cumulants, this is different. Cumulants have different properties from these. So, okay, I always need to define this because the binomial is defined as a over alpha is a factorial divided by alpha factorial and a minus alpha factorial. Yeah, so there's the definition. Okay, if you use this function here, I've written it in 3D. If you use it in 2D, for example, this K20 will turn out to be M20. So you see when alpha equals A, then these things here will all be 1, yeah, because they taken to 0 order, yeah. So we'll always have, so they always look like this. The central moment is the same raw moment plus or minus something else, and this something else is a polynomial in velocity, yeah. So what comes out is minus m10 squared divided by m00. And this can also, I mean, obviously be written as m20 minus u square rho squared divided by rho, yeah, so that this finally gets m20 minus u square rho, as an example. Sorry for my voice. Other example, K11 becomes M11 minus UV rho. So, what does this, for example, what does this mean for the equilibria? For example, look at what is M20 equilibrium. Yeah, so this is U square plus theta rho, right? So that would imply that the K20, so what is the equilibrium of K20 now? U square rho. M20 in equilibrium. Yeah, so this is, we have U square rho plus theta, yeah? So now up here, we have the difference between the moments. So what is left? Theta rho. I mean, there's something, okay, and do the other two. M11 equilibrium equals to U V rho. Well, we get this minus U V rho. So implication is sorry, that was not that. K11 equilibrium is 0. So very important and big difference to what you see in MRT. So if you look at in the paper of the MRT and look at the equilibria of these moments, they are all functions of velocity and density. Yeah, and this is not the case if you use that's not true for central moments, and also not physically. I mean, not only for the Lattice Boltzmann method, but also for the Boltzmann equation in general. Yeah, that the equilibrium of central moments is not a function of velocity. Because in central moments, velocity is 0. Yeah? So you are in a frame where your velocity is 0, so it cannot depend on velocity. Yeah? Okay, I wanted to write down the definition of Galilean invariance that you've already given us. Galilean invariance. Frame of inertia. If I could write this, of inertia must not influence the behavior of the system, by which we mean the equations are agnostic to the, okay, I mean, that's again a difficult explanation. So the equations of motion don't change when you go to a different inertia system, but the system needs to be inertia, so it must not be under acceleration. Yeah. So let's do some science and investigate. The question is MRT Galilean invariant? Okay, we have not checked yet. So in order to know, we have to check through all the moments, and I have to, okay, before I go on here, there is of course a caveat. The method works on a lattice. Yeah. So we have a given system in which we describe our velocities, and this is very, very finite. So we have only 9 speeds, for example, in 2D. So there is no way on Earth that this could be truly Galilean invariant. Yeah. But there is, of course, a measure of degree how you could do things wrong. Yeah. Yeah. So we are in the we say we are in a post-factual time. Yeah. So there is in modeling there is always a level of truth. Yeah. And now we're interested in on what level of correctness are we. Yeah. So and for this we look at a few specific. So we don't do it in general. We do it by example, and you know that I know the right examples that hurt. So we start with one that does not hurt. Yeah. So let's look at raw moment relaxation in central moments. Okay, what am I doing? My idea is I look at an MRT collision operator, which is now a little bit unusual because I'm not using the pressure one, but I just take one of the moments that I would usually not relax on its own, namely M to 0, yeah, but doesn't matter here. So I'll write down what I would do in an MRT. So I would have a relaxation rate for that specific moment. I would go into the equilibrium here, and I would subtract the pre-collision state and come to the post-collision state in that way. Yeah. So this is what I would do. And now the question is, what would this thing that is done in raw moments do to the central moments? And we would like it to behave the same way. So what we do is we have 3 different raw moments here, namely the post-collision state, the pre-collision state, and the equilibrium state. And all of them we will transform into their central moment counterpart. Yeah. So, and this is done because okay, I'm taking this because we've already done this, yeah? So K20 is M20 minus this thing here, yeah? So this means I can replace M20 by K20 plus this thing here, yeah? And this I can do for the pre-collision state, the post-collision state, and the equilibrium state under the assumption, there's an important assumption that there is no force. Yeah, so that velocity is, does not change during collision. Yeah, so that's our assumption. So, but it's a reasonable assumption for that moment. Okay, so we'll replace these. So we'll have K at this M20 will become, after collision will become K20 after collision. Now plus, the other way around, U square rho. So these are collision invariants, so nothing to change here. Then on the other side, we have the pre-collision K20 plus U square rho plus omega 20. Now we have M2, K20 equilibrium comes again plus U square rho minus K20 pre-collision minus U square rho, okay? Is this correct? So now what we observe is we can eliminate this here with this here, and we'll eliminate this here with this here. So what comes out is K20 after collision is equal to K20 plus omega 20 K20 equilibrium minus K20, and now we can be happy. Apparently these guys were not completely stupid who invented this, because this moment is indeed frame independent. So it does not matter whether we do this in a centered frame or in any other frame, we get the same result. So, by the way, the same, okay, the same is true for all the second order moments, which I'll not check. We are not going to check all of them. Of course, you can do this if you, all second order moments. So that would be K20, K02, and K11. So they are all Galilean invariant. So makes sense because MRT actually works, yeah, and so should be the case, yeah. So, well, what about the third moments? The third moments are ghost moments, yeah. So we know that they are not very important for the equation that we solve, but we've also already seen that what we do with them has some influence on the stability and other things. So now we are interested in how they perform. So third moments. Let's take K21 is equal to M. Yeah, right. So we first have to write out what. Okay, when we do the binomial transform, this K21 becomes M21 minus 2UM11 minus VM20 plus 2U square V rho. Now immediately we should observe a difference here. So this thing that we had to add to the second moment, this was invariant under collision, yeah? Like this. This is also collision invariant. However, here we have moments that change in collision. So I'm not sure whether this is a correct English word, but if one thing is invariant, then the opposite of this is variant. Yeah. So I just call this a collision variant. Yeah. So these things also have to be translated into central moments. So for example, we have M11 is K11 plus UV rho, and this M20, okay, we had this K20 plus U square rho, which means if we plug this into the above, what we get is that M21 becomes K12 plus 2U K11 plus V K20 plus U square V rho. So I've taken this now from my notes. I hope it is anyway correct. So the reason why, you see, there was a 2 here, but because there is, for example, there is UV in the equilibrium part of this one here, yeah. So there's a compensation with these two. This is why in the end we'll end up here without this 2. So what we do now is, with this knowledge of how to translate the raw moment into central moments, we again look at what we would do in MRT. So we'll do the relaxation in the Euler frame. Here we have M21 after collision is M21 before collision. There would be relaxation rate omega 21, M21 equilibrium minus the state before the collision. So now we'll replace all of them. There's a lot of writing going on, and I don't have any page left, so I go to the next page. So we'll have to replace this thing here by all of this, unfortunately, yeah? And now what is important, if this here is, for example, the pre-collision state, then in the post-collision state, these K, of course, will also become post-collision state, yeah? So it's the translation in this particular state. So we'll have K21 post-collision plus 2U K11 post-collision plus VK20 post-collision plus U square V rho. So this was all just the left hand side of this, yeah? Now the other side. We have a lot of writing because we have to do the same thing again. Now the only difference is that this thing here is the pre-collision state. So we'll come out with the pre-collision here, K21 plus 2UK11 plus VK20 plus U square V rho. So that was this one. Now we get into plus omega to 1. Now come the equilibrium part of this. So here we have 2U K11 equilibrium plus VK20 equilibrium plus U square V rho. So that was this one. And now again comes the pre-collision states, which we subtract K21 minus UK11 minus VK20 not equilibrium minus U square V rho. Okay, so again, the parts that are collision invariant, they drop out. So this here drops out against this, and this here drops out against that. Yeah? So, but that's not all we have. Now we have a little bit of problem. So what are we going to do with these post-collision states here? So for the post-collision states, we use that K20 after collision is K20 before collision plus omega 20 K20 equilibrium minus K20, and K11 after collision is K11 before collision plus omega 11 K11 equilibrium minus K11. So this is what we plug in here. So we get K21 after collision plus 2U Okay, so yes, because there's a lot of writing, I'll already cut a few things out. So what we observe is that K20 always comes as something that after collision is always something before collision, yeah. And this thing before collision we already have on the other side. So I'll not write down this, and I'm not going to write down this here because I'm already canceling these against each other, right? So I'll end up only having the reminder, which is this here, and on the other side, these two last lines, yeah? So I'll end up with omega 11 K11 equilibrium minus K11 plus V omega 20 K20 equilibrium minus K20, and this being equal to K. So now everything else here has disappeared up to this here, of course, plus now the last two line, omega 21, K1 to 1 equilibrium minus K21. So I'm grouping together this here with this here. Yeah, so I'm grouping the equilibrium minus the non-equilibrium together. So here I have U K11 equilibrium minus K11 before collision plus V K20 equilibrium minus K20, and that's it. And now I'll rearrange it slightly again, putting everything on the right hand side. So I'll have K20 after collision will be K2. Why do I say K20? K21. Yes, sorry for my. I mean, it's amazing that I always write it correct, right? K21 after collision is K21 before collision. So now I'm already grouping it like the way I want it, yeah? So because what I observe is I have this thing here, and I actually want this to be related to these two guys here. So I have omega 21 K21 equilibrium minus K21. So I write it like this because this is what I want to have. Yeah. So this is what I would have if I did the collision in the Lagrange frame. So if I did it with central moments instead of raw moments, that's what I would get. Now, that's not all that is written here, right? So we have, on the one hand, we have these things here, and on the other side, we also have these things here. So they look similar. They have a 2u blah in front of them. However, there is they are both coming with plus. Like they look like they would cancel out. But there's a difference here, and this is to do with the relaxation of the different moments, because this has the relaxation of this second order moment, and this here has the relaxation of the third order moment in front of it. So we'll end up with plus u omega 2 1 minus, because they have the same sign, I put them on the other side. So there's omega 2 1 minus omega 1 1 into k 1 1 equilibrium minus k 1 1, and plus v omega 2 1 minus omega 2 0 to k 2 0 equilibrium minus k 2 0. So, and this is of course not Galilean invariant. This is a violation of Galilean invariance. There should be a, okay, so there should be a 2 here. Yeah, you're right. Okay, so what I said before, we are living on a lattice, and on a lattice there will never be complete Galilean invariance. Yeah. However, what we did here did not consider the lattice, right? So we never assumed a lattice. We never assumed that this is that there is no further moments going on. We never assumed this, and it's still not Galilean invariant. So even having an infinite lattice with infinitely many speeds, MRT would still not be Galilean invariant due to this behavior. Okay? Okay, this is so important that I'm going to write it down. Wait, I wanted to write two things down. First this. So the third order moments, they are not Galilean invariant. In the classical, so classical in this context means in particular using raw moments. Okay, before I come to this other point, I want to point one other thing out. Because we like to bash BGK, because BGK is not very stable, but BGK obviously has an advantage. So what happens in BGK? In BGK, omega 2 1 is equal to omega 2 0 is equal to omega 1 1. Okay? So, and what does this imply? So these things here are Galilean invariant only under the very condition of MRT, which is relaxation rates are different. Yeah? So there is a lame excuse that you'll often hear from MRT people that if you don't like it, you can put them the same. Yeah? So, but I mean, what's the point? Yeah? So here, of course, if you put these things here the same, then the Galilean invariance will disappear. Because BGK is Galilean invariant. Should write properly. Okay, BGK is not all bad. BGK is Galilean invariant where MRT is not. So, yeah, so the other thing that I've just said, but I wanted to write down, is that the violation of Galilean invariance is not due to discretization. I mean, there is a violation of Galilean invariance due to discretization, but here we discovered one that comes on top of whatever we have in discretization. Yeah, the reason, so we have not assumed any discretization in the analysis here. So we have not assumed that there are ghost moments or anything like this. So now we have these two problems. First of all, we'll have we have to use a very specific orthogonality to our. We would have to use a very specific orthogonality to make our moments independent. If we use Ra moments, but then they are not Galilean invariants. Reversely, if we make them Galilean invariant by using Ra moments, it is not clear how we make them independent of each other. Yeah, because for every moment, for every time that we define a different frame of reference, we would have to find new weights for the moments that make them independent. Yeah. So now the question is how can we do both of these things together? Yeah. And this comes here with Laplace asking the question, are moments, Laplace is always the one that asks the questions, really the best choice of variables? So in the last 10 years, something, I mean, you know that I'm going to say no, yeah? But actually, the question also is cumulants are the best choice. I mean, cumulants is the best choice that we have found so far. Yeah, but there is still a lot of things unclear. But okay, we'll look in what is the state of the art now. Yeah. Okay, you have a question? Yes.
Before we move to cumulants, could you explain more how it's invariant due to discretization? Are we with
yeah. Okay. Very simple. So we have. I mean, there is so the way it is violating Galilean invariance due to discretization. The very obvious thing is that we do not have an independent moment M30. Yeah. So we don't have this moment. So we had to assume we had this already. We had to assume that velocity is small, because you remember that moment, even in equilibrium, that moment should be 3 theta u, yeah, which is the part that we get by aliasing, plus u cube times rho, which is a part that we are missing. Yeah, and this is violating our Galilean invariance. And another part that we are missing is the non-equilibrium thing of this, because we are, there is no non-equilibrium because it's always equal to the first moment. And this is true for all following moments. So this is how they will always violate Galilean invariance. Okay, so this is one way of looking at it. And if you want to know what this physically leads to, so physically, I mean, or the moment, the model. So what we already know is we have to fix the velocity, the temperature. Yeah, otherwise we don't get the right aliasing. So we'll have to fix the temperature. and we do not have heat flux. So we cannot conserve energy. We cannot define heat flux. And if we forget about this and think only in isotropic terms, then there's also an effect on this. And the effect is that we observe that viscosity becomes a function of velocity. So viscosity is not Galilean invariant due to discretization. There is a partial correction to this, which is a little bit advanced, and we'll not discuss it during the lecture. If you look in the papers, you'll find an additional term that also contradicts a little bit what I was saying here, that the equilibrium, so I claimed that the equilibrium should not, for central moments, should not depend on velocity. Yeah. So what sometimes happens in numerics, if you have a discretization artifact, is that you can do something, you can enter a counter term. Yeah. So, and in fact, it is possible to enter in the equilibrium of the second order moments a counter term that will compensate for part of the error that you generate by ignoring the third order moment, such that your viscosity is no longer dependent on velocity. However, this is only a partial correction, because there is another problem with this, is that you have a small phase shift. Now you see this is going very, very, very advanced. Yeah. So it's actually not part of the lecture, but it's actually not so difficult to do. Coming to cumulants. Yeah. So what's so what's our starting point here? So we have seen. So one thing that we want to do is we want to relax different moments. We want to give different moments different timescales by relaxing them with different rates. Yeah, but in order for this to be reasonable, they should be independent of each other. So independent they should not, one should not change together with the other. Yeah. And because if two things change together, they would usually behave on the same time scale, right? So then it makes sense to give them the same time, which you can do with MRT by identifying at the end of the day, if you want to have it Galilean invariant, it has only one relaxation rate. Yeah, because if you do not properly decouple these things, yeah, so then you have to make them all the same. Otherwise, you're violating Galilean invariance. So in order not to couple them, they need to be independent. So they need to be variables that do not correlate with each other. They do not change at the same time, proportional to each other, right? So this is, or you could say in inverse, if variables are not independent of each other. Why is this computer making such a noise? Am I still, wait, small check, yeah. If they are not independent of each other, their relaxation time should be coupled. And this is not what we want. I mean, you can also say, okay, I should say some people want this. I mean, like, some people really, really, really want this. And the reason for this is people dislike it when a model has unfixed parameters, right? So now there's a little bit the problem of MRT. Yeah, you have more parameters, but they are not in the governing equation, so they are open parameters. So they are not fixed, so you have to choose them. So now depending on what is your background, you can love freedom or you can, love clarity. If it's not, because now you have the freedom, but the freedom is a problem. Yeah, freedom is always a problem. Unfortunately, yeah. Strangely enough, I'm very much in favor of freedom. As you can see, I'm a disgraced professor who is defending his institute, which should have already be closed down, and we are still standing like a rock. Yeah. So I love freedom, yeah, but freedom also comes with a cost. That you have the choice and you have to choose. So now, what does independent actually means? So what are independent random variables? So the idea behind using how are we doing in time? I'm too slow. The idea behind the orthogonality in MRT was, when I make the matrix orthogonal, these things are uncoupled, yeah, and so they're independent. Now, we tested this hypothesis, and it was not true, right? So we have to be more specific what that would mean. And actually, it is a bit complicated in detail. So, I mean, there is, in the conferences, there have been over the decades, you could now say, always discussions, and they are not over and not completely clear now. Yeah. So, but what we usually mean with independence of variables is, if we have two variables, say we have a random variable x, which in that case would be, for example, the velocity of a particle in x direction and the velocity of the particle in y direction. Yeah, and when these two things would be independent, so there's only an example. Yeah, but if these two things are independent of each other, then that means that if we have knowledge, so we have a measurement. Knowledge means there's a measurement of the state of x, then this implies no knowledge on the state of y. This, and I mean, this is in a statistical sense. So now, I mean, you've seen in the last week that the temperature that we have here depends on the direction of the wind. So when wind comes from north, in Europe it is cold. Yeah? If wind comes from west, it is relatively mild. That is in winter. In summer, it's a little, so it's not completely coupled, because in summer it would be hot if wind comes from the east. Yeah, and it would be relatively mild if wind comes from the west. However, these things are clearly coupled. So, meaning when I look, when I know the direction of the wind, if I have knowledge of the direction of the wind, I can make a guess which is better than nothing about the temperature. So these two things are not independent of each other. Yeah? So we'll have to find something that makes knowledge on one variable implying no knowledge on another variable. And these independence we have to construct. They are not dropping from heaven. So now how could we possibly do this? For this we go back to our moment generating function. So moment generating function is the it can be the Fourier or the Laplace transform. They behave the same way. So this, I usually prefer the Laplace transform just because they're easier to write down. And hereby I mean the Laplace transform. So in the bidirectional Laplace transform from minus infinity to infinity over f of small xi into e xi, small xi times frequency xi, capital Xi, integrated over xi. And everybody familiar with the Laplace transform, notice there should be a minus here, but for whatever reason, this is the other way around. So this is basically the inverse Laplace transform with different sign. Yeah. So unfortunately, otherwise, I don't know. All the velocities in the universe would be defined with a minus, and this is strange, and this is why we'll have no minus here. Yeah. So now, so this is just taking the Laplace transform of this function, and now this distribution, and this distribution should be described by moment. So I could say that this function is also a function of moments. Yeah. So because V is generating the moments. So, and actually what this is, because the F is a probability distribution, we just turned this probability distribution into another space. So we had the distribution in the velocity space, and now what we do is we have this distribution in a kind of a frequency space. It's a little bit strange what this is supposed to mean, but it's the frequency in velocity, if you like. Yeah. And one thing that I like about this, I don't know whether this is really important, but suppose even that here would be a discrete function. Or discrete, like suppose world would not be continuous, but we would have something like atoms flying around. So there would be velocity pulses somewhere, and we do the integral over them. We do the Laplace transform. We get a continuous function anyway. Yeah. So, and because this is having a continuous function is important for actually making a series expansion. Yeah. So you cannot easily expand something that is discrete. Not continuous. But even if it's not continuous, the Laplace transform of this is continuous, and so it can be expanded. Yeah. So now we have what we basically have. So this is a probability density. Now we have a probability density in a different space where it is continuous. And so what we know about independence of variables is that their probabilities and also their probability distributions, they factorized. So we have factorization of the distribution, because we have a factorization of the probability. Yeah, so you know, when you have independent random variables, so the occurrence of both together is the probability of the one times the probability of the other. So we have the factorization. This is what we call independence. Now, this property we want to obtain. We want to find the variables that have this property. Yeah. So let's see how we could do this. Okay, I'll remind you that this xi is the vector that we write. So my definition, yeah, vector xi has the first component xi, the second component ypsilon, which is a letter that I absolutely cannot write. So this is supposed to be a large epsilon, and then there is a theta, large theta. Yeah. So the moments taken from the moments of the moment. So how do we get the moments? The moments are the coefficients of a series expansion. So series expansion, basically a Taylor expansion. So what do you do for a Taylor expansion? You take the derivatives of a function at a development point, yeah, and then you build the polynomial and add these up. So first we have to take these derivatives. And actually the values of the derivatives, these are the moments. So we've already seen this here. We take the 8 level in the xi direction. Then here the beat derivative in the epsilon, and the seed in the theta of f of xi. And then we need a development point, and the development point is we define at frequency 0. Yeah, so this is exactly what we do in a Taylor series. So inversely, now we can write this Taylor series. Yeah, so f as a Taylor series. Yeah, always assuming that's possible. Yeah, mathematicians will discuss whether this is possible, whether they exist or not. We'll do the assumption they exist. Okay, so suppose they exist. Suppose they exist, then we can write this f as the Taylor expansion A, B, C, so Taylor series, going from, so over all the moments, because all the moments are all the derivatives, yeah. So we have to use this polynomial in xi by the power of A, epsilon by the power of B, and theta by the power of C. And then there is one thing missing from the moments, and this is just a part of the definition, namely the factorials. Yeah. So they are not in the definition of the moment, so but they are in the Taylor expansion. So and then we add up these moments. Yeah. So this is so to speak the inverse definition. Yeah. Here you see the moments are simply the coefficients of this Taylor expansion. Now the Taylor expansion, unfortunately, or the Taylor series is a series, so it's a sum over everything. Yeah, so they are not separated the way we want them. What we want is that we have something that can be written as a product over these variables. Now we have variables, but we have a sum. We need a product over something. So how do we turn a sum into a product? Okay, so I give you some time for thinking. for independent. So for independent variables, what we would have is we have our f, where there's all the information in it, and we want this to be the probability distribution of joint variables. Yeah. So then we propose that this can be written as a product from 0 to infinity over something fi that depend for variable ci, right? And these ci are the independent variables. We don't know how they look like, but they have this property. So now we have this product. What we know how to do is we know how to do a sum. Sum to product. Okay, last chance. The logarithm. So what we do is we take the logarithm of f of xi, right? So this will give us a sum from I to infinity over the log of fi ci. So what is the implication? If we do a Taylor series expansion, not of f, but of the logarithm of f, the things here, they should be independent variables. Yeah, they have this property by which we define independence. Okay. So let's see what. Okay, let's just use this as a template. So log of f in xi is equal to the sum. So suppose there are variables that have this behavior. So we sum over ABC to infinity, and there is xi a epsilon to the b and c to the c, theta to the c, a, b, c, and and suppose there are variables c, a, b, c. So large c, yeah, small. This is small c, this is a large c. There are not enough letters. So if this is how we would do the Taylor series, then going back, I mean, we had this template and we also had this template. So if we inverse this again, what we end up with is that we can say that CABC is equal to the derivative or the derivatives in these three variables and the logarithm of f of xi at position xi equal to 0. Yeah. So that's the theory. Now these are supposed to be variables that are independent. So the idea now is we use these things here as variables, MRT with cumulants. So what they should do is we have independent variables and we have Galilean invariance. So now I have to admit something. The idea to use cumulants for Lattice Boltzmann is much older than we are actually able to use cumulants for Lattice Boltzmann, because if I remember looking in a book, it's almost 20 years ago now, yeah, how to compute cumulants by Gardinger, I believe, and I always remember this sentence. saying that there is no easy way to compute cumulants. I mean, this is what you have. This is what apparently you have to do. You do a Laplace transform, take the logarithm, and then take the derivatives. Yeah. So if you try, if this is your starting point, it's absolutely not clear what you should do. Yeah. So let's come to how this is actually. Okay, we're not coming to today. We're not coming to how it is actually done, but only to how it can be done. Yeah, yeah. So we need a little bit more details later, but not today. So computing cumulants. So let's think about it. We have C. Let's start with this one, C001, right? Now, by definition, so the first two derivatives, they will disappear, and we'll just have the first derivative in Z on the logarithm of f of xi at the position xi equal to 0. So if we want to do this directly, it could be horrible, but there is something that helps us, and the thing that helps us is the chain rule. Yeah. So we'll apply the chain rule a lot, and the chain rule in that sense, we first take the derivative with respect to f first, yeah, the logarithm, and then what we come up with is that this is 1 over f into d set f, right? And this still at xi equal to 0. Now what we have to understand is, so this xi equal to 0, this gives us the actual moment. And what we see is that we have two moments. Here we have the f not without any derivative. Yeah. So f without any derivative at position 0 is the 0 moment. Right? Yeah. So we'll have down here, we'll have m000. Now above here we have the first derivative of f, which is the first moment. Yeah. So we'll have m001 divided by m000. m001 is the momentum, rho times w, and this divided by the momentum comes out as the velocity. So something else. C002, so this is the second derivative of the logarithm of f c equal to 0. So what we are going to do is we'll take this guy here and just take another derivative in z direction. So end up with the first one here being minus, so we'll take, so that now we, in addition to the chain rule, we get the product rule that we apply, and this becomes minus f squared down here, and d theta f square plus here the second derivative in f divided by f, and this again evaluated at xi equal to 0. Now we'll have, so the second, yeah, so I miswrote here. So here, this here will identify as a second moment. This here is a first moment squared. Here is a 0 moment squared, and here is a 0 moment. So what comes out of this is minus w square plus M002 divided by M000. So, you know, there is in this M002, there's a W square in it, right? So this will disappear and we only get the central part of the moment. Yeah, so this automatically gives us, this is a central moment already, right? So what we actually have here, so this is, and this is pretty interesting, if you will. By the way, the inventor of the guy who discovered moments, I think his name was Karl Thiele, I believe, like our professor here, or Thiel, not a German. It was Scandinavian, I believe. So it is said that he had the problem that whenever he talked, nobody understood anything. And that's probably because he talked about cumulants. So cumulants seems to be a thing that is apparently difficult to grasp. Maybe you can agree, maybe not. But there is something extremely funny about this. So you see the equilibrium and of this trace of the second order moment, and you know this is related to the energy, so that would be conserved in a sense. So it's not actually the energy, but what you see is the temperature. So there's something that directly gives you the temperature. Yeah. So you see, you don't get the momentum and you don't get energy. What you get is velocity and you get temperature. And if you think about this and think that potentially cumulants are something complicated, you should also think reversely that what comes out of cumulants is exactly the stuff that you observe in nature. Yeah. So we always knew what temperature, something is hot. Yeah. So something feels hot because it is higher, it has higher temperature than your hand. Yeah. So what is temperature? Is it energy? Well, then there is energy capacity. Yeah. So also velocity. What is velocity? Is this momentum? So velocity is basically when two things have different velocity, then they exchange momentum. If two things have different temperature, then they exchange energy, right? So it's something that you directly feel when it's always difficult somehow to explain, to define. And now comes cumulants, and it becomes very easy. Cumulants are just these things. Yeah? So, sorry for getting emotional. Cumulant, so first cumulant is the velocity. You also see these intensive quantities, yeah? When moments are extensive quantities, these are intensive quantities. So they are not conserved because intensive quantities are not conserved. Yeah? Because there's not a flux of intensive quantities, there's only a flux of extensive quantities. So trace of second order cumulants, this is the temperature. Now there are infinitely many other cumulants, but what we observe here, and this is, I believe, it's a little bit controversial, this one, for a mathematical reason that I don't want to get into, in particular because I don't understand it. The equilibrium of all higher cumulants is 0. I mean, this is, if you take the Maxwell distribution, yeah, and compute the cumulants of these things, all the cumulants are 0, just not the one for temperature and velocity. Okay, running over time, even though we don't have too much text. So cumulants and their relation to central moments, or cumulants in central moments. Okay, this is one thing that we'll have in a later lecture, not necessarily next time, but later we'll discuss this in a bit more detail, what advantages or disadvantages this may have. Okay, so what we are going to do is we look at the change. So we'll look at, okay, maybe I should say this here. So using this method, yeah, of the chain rule, we find how we can write cumulants in terms of moments. Yeah, and now of interest is how does this relate to the frame of reference in which we compute these moments. Yeah, so and the change of the frame of reference according to the translational rules of the Laplace transform. So I really hope that you learn a lot of Laplace transform and their properties in your math lectures, because these transforms are very, very useful, have very, very useful properties, and can be very helpful if you know how to deal with them. So it's very important knowledge, yeah. So, so what happens? So what happens if you change the frame of reference in a Laplace? Okay, I'm a little lazy and say that this is from Euler to Lagrange. What is actually more accurately, it's from one to the other. Yeah, so from one frame of reference to another frame of reference. Yeah, so say in the Euler frame we have F. So and then we go to another frame. How do we translate this from one frame to the other? And if you look into the definition of the Laplace transform, it is not so difficult that you see is that you'll have you multiply. So the translation of the function is a multiplication with this e function, yeah, with this exponential function, where again the sign convention is opposite to normal, yeah, because to the normal transform, or to the standard transform. So what does this mean? Okay, you have seen this. Yeah? Yeah, okay. So what does this mean for the cumulants? So if we have the definition of the cumulants, so now let's have the logarithm of f something e u times xi, and this at xi equal to 0 vector. So because it's the logarithm, I can put this into a sum. And if I take the logarithm of this thing, of the exponential function, I'll end up so what I'm ending up with is I can write out u times xi plus the logarithm of the rest here. And this evaluated xc equal to 0. So now what does this mean? This means I can shift the function arbitrary, and all that changes is here this monomial, or the linear term. What happens to the linear term? And here it's important, of course, that you first do the derivative and then you enter this. So you first do the derivative. So because this is linear, only the first derivatives will be non-zero, yeah, and they will not contain any xi anymore, so they will stay here. So only the first cumulants depend on the frame of reference, yeah. All the other cumulants are independent of the frame of reference. Which is a good thing for independent variables, yeah. So all but order 1 cumulants are frame independent. Now there is a practical application of this that helps us gaining some efficiency. So because this transformation between moments and cumulants can get very, very complicated for higher order cumulants, yeah. And now we make the observation that writing cumulants in terms of central moments is more efficient than in terms of raw moments. So I show you what I mean. So we have C 002 is equal to M002 divided by M000 minus M001 squared divided by M000. So this is coming out of the above. So since the cumulant, the second order cumulant, does not care in which frame of reference it is taken, the same that applies to the moments in this one frame of reference also apply to the moments in the centered frame of reference. So this is strictly the same. Okay, they are the same. However, all the first order central moments are 0, right? So this here is, these guys are 0. So what we can do is we can say that this simply is K002 divided by K000, right? So whenever we have an equation for the cumulants in terms of moments, if we take the central moments, we can delete all the terms that come with the first order moments, and these are usually most of them. Yeah, so they are then getting small, much smaller pretty quickly, even though there's still a lot to do. Okay, now we'll have to do as the last proper thing for this lecture is to actually show that we solved our initial problem that we have been starting with last time, testing cumulants, yeah? And for this, you have to recall the problem. And I mean, this is a real problem that was holding back the Lattice Boltzmann theory for a long time. The moment M211 in the D3Q27 velocity. Yeah, so we looked at this, and in practice, the observation was that we get either overdamping, so very inaccurate results, or instability, depending what we do. So depending on whether we use non-orthogonal moments or unweighted orthogonal moments, we could either get overdamping or we could get instability. And okay, now my text is a little bit inaccurate, but I leave it at this. So there were two, I said there was only the way, so we had to change the moment to M to N, so N211 and relax this, and we call this M211 minus theta M011. So of course, what is also a possibility is if you take all the relaxation rates the same, yeah, then you would also eliminate this dependency, yeah, but this is not what we want to do. So now have cumulants solved this problem? Suppose we are not relaxing this, but we are relaxing the cumulant 2 C211. So what is this cumulant? C211 expressed in central moments is K211 divided by rho minus K200 times K011. Now, by the way, so this never happens with central moments. Here we have a product of two non-first order moments, yeah? So, I mean, this does not happen when you transform from central to raw moments, yeah? So there's only a polynomial in the first moments, not in higher moments. Here now we get a polynomial in higher moments, yeah? So plus 2K110 times K101, and this divided by rho square. So now this is a little bit a complex problem, so we'll simplify this to the order to which we were caring, yeah, and we were caring for this problem up to second order, because this is where the problem occurred. So second order in diffusive scaling. So what happens at second order to diffusive scaling? So in order to do this, we'll do the expansion of this moment we use the moment to second order, yeah, meaning that everything on the right-hand side now has to be second order. So how do we get this? So this K211 to second order divided by rho now to zero order, yeah, otherwise so that they together are second order, minus, now we have to go through these guys here. This is K200. If this is to second order, then the other one has to be to zero order in order to have this second order both together, yeah, because they are products, yeah. So that's also if this here is to first order, then this here is also to first order. And then, of course, we have K0, 0 to 0 order and K0, 1, 1 to second order. Plus 2, okay, I'll take the 2 out, K1, 1, 0 to second order times K1, 0, 1 to 0 order plus K1, 1, 0 to 0 order times K1, 0, 1 to second order plus K1, 1, 0 to first order times K1, 0, 1 to first order, and all of this divided by rho to 0 order. Okay, now many of them do not exist. Yeah, second order central moments, they do not have. So these guys here, yeah. So non-equilibrium to second order 0, right? Equilibrium is U times V, yeah. This each of them to 0 order would be 0. So this guy and this here to 0 order, they are 0. So have a drop out here. No, that's not. This is something else. So, but we'll have a drop out here. We'll have a drop out here. Okay, these here, first order, they are also K1, 1, 0 to first order. This is also 0. Yeah? And you do the asymptotic analysis. So they are also dropping out. So the entire thing here is dropping out. And this here is also dropping out. So there's only one thing left, namely the K20. K20 to 0 order. What is K20 to 0 order? This is rho to 0 order theta. Yeah? So we have this constant. We divide by rho again. So what we'll end up is C211 to second order is K211 to second order divided by rho 0 minus theta K011 to second order divided by rho 0. Now this is what we do the relaxation on. And what you observe is that now in the Lagrangian frame of reference, so this is this is anyway not Galilean, would not be Galilean invariant because it's defined in the Euler frame, yeah, but otherwise it's the moment M211 minus theta moment M011. And to the order that we care, this is the same, yeah. So this automatically drops out when we relax the cumulants, yeah, they make themselves directly independent in this way. So this means that here the cumulant removes MRT problem. So meaning what we can now have is we have a free choice of relaxation rates plus we have Galilean invariance to the extent allowed by the discretization, of course, right? So, okay, so like you always tell me that I'm doing to not enough lecture because we'll have 3 hours. This is the proper lecture for today. Now there's at least one additional thing, because I was asked to talk about momentum exchange. And there's of course two things that we could do now, and one thing would be we implement momentum exchange. And I was thinking, well, if I do this, I've more or less done all of your homework. So I'll not implement it for you. I'll just tell you, okay? And then you do it, you'll still do it yourself. Okay, so this is now the lecture. The lecture on cumulants is done, and now we have a small add-on here on momentum exchange. So why do we use momentum exchange? I've not prepared a lot, so I'll mostly talk now. So what mostly we do with computational fluid dynamics is calculating forces that act on bodies, right? So this is where computational fluid dynamics basically comes from. So what still is the main application of computational fluid dynamics is to calculate the CD value of cars. This is still what CFD is more or less invented for. So in order to do this, so the CD value is basically a normalized force. Yeah, that's you can look this up on Wikipedia. I'm not writing this down now. Yeah, it's not that fancy. So you have the force divided by the density, the size of the system, and the velocity square kind of thing. Yeah, so that you get a dimensionless number for. Depending on what direction, it will either be the lift or the track. So, but in order to calculate this, what you need is to know the force that is acting on the body. And in the Navier-Stokes equation, if you're familiar with this is done by integrating the stress over the contour of the body. And the reason for doing this is because the Navier-Stokes equation solves for the velocity, for what they call the primitive variables, which we now learned are actually cumulants. And this is not directly a flux of momentum. So there are different terms. So you have a pressure in there, and you have a viscous part, so a shear stress on it. And what you have to do is you have to integrate the pressure over the surface and this and the shear what's it called, the stress tensor, the stress. So, and you have to do this over the surface. So it is actually pretty annoying, because to calculate the shear stress directly on the surface if what you have is the velocity. Because what you do is you take derivatives of the velocity, and if you do this directly on the surface of a body, then you only have part of the domain. Yeah, so you cannot easily apply finite differences to this. Yeah, because one part of the domain is not part of the domain. Therefore, calculating forces on bodies in the Navier-Stokes equation is a difficult thing to do. And this comes a little bit in surprise, because lattice Boltzmann is in a lot of sense more complicated, in particular on the boundary. You cannot, so you always have to think about, so what does this physically mean? You cannot just set Dirichlet and Neumann boundary conditions, how you do in other differential equation things, because velocity is the outcome, it's not a variable that you're solving for. So you cannot just set velocity somewhere, you cannot just set pressure somewhere. However, what you have as your primitive variable is this distribution f, and of this you can take simply the moments, the second moments, and then you have, then you have the momentum flux. And you don't even need to do this, because you can in a very primitive sense, ask what is the momentum that goes into the body and what is the momentum that goes out of the body. Yeah. So all you need to do, so basically what you're interested in, you want to have F, yeah, and F is the change of momentum, yeah, in time. So how does momentum change? So you have momentum that flows from your domain into the boundary, and you have momentum that flows from the boundary into the domain. And what you need to do is to add these things together. That's all you need to do. So that basically, yeah, say, okay, that we have another nabla here. All you need to do is to integrate over all momentum entering and leaving the domain. So you have to take both, yeah? Maybe not the domain, the body. The body you are concerned with. Okay, our usual picture. So say this is X and this is T as always, and here we have this is very ugly. Here we have a wall, and here we have our lattice nodes. So there is now something is going out, and say at the same time or the next time, don't be too accurate here. So and then there is something is going in. And say this green one, this I now call, I'm not sure whether I'm always consistent with this. I say that this is the positive direction, this is Fi, and the red one is the other way, this is F minus I, right? So now, what is the force that is acting on the body? The force that is acting on the body is formally you have to add, in order for it to be a force, yeah, you have to add a mass, yeah. But later, if you compute the CD value, you also divide by the density, so there's a mass again. So if you just want to compute CD, you don't need this mass, right? So you have a mass in principle, and then you sum over all the I on the boundary. I now indicate the boundary, so have the boundary as gamma. So everything that goes in and out to the boundary gamma. Yeah, I in gamma. So by so this means not for one node, but for all the nodes. Yeah, all the nodes that enter here. So there you have Fi. Now this, of course, this is now the population. What we need is the momentum of the population. So the momentum, we already have the mass, so we need the velocity of this. So this is Ci. But if you want to know how this thing changes, you also have to subtract the velocity of the body from it. Yeah, so I mean, when everything is in state, not stat. Yeah, I mean, if everything is moving with the same velocity, then there's no change in momentum, right? So now this is basically what is going into the body. Yeah, so I should have potentially written this in green, but I don't want to change it now. So let's write the other one in red. So because there's also the thing that is going out, and this we have to subtract. Yeah. So there's this F minus C in the other direction. So C minus U. Yeah. So and now this, you see, we will have a population that leaves the fluid and goes into the body, and then what is entering it. For example, if you have bounce back, then they are both the same, right? Yeah. But if you have a different boundary condition, they may be different. So you have to know what you're doing. Yeah. So and now this CI is exactly the inverse of C. So can write this again in the way M, the sum over I in the entire boundary, Fi, Ci minus U. Now I'll take here now a plus because I'm inverting this, and then I also have to, so then because I replace C minus I with Ci, and then I also have to change this because there are two of them. So basically, that's all there is. Yeah. So you only have to add these up. Now, if you have a static body, so in your homework you have a static body, then this thing does not have a velocity, so the velocity drops out. So what you have is simply the sum over everything that goes in minus everything that goes out. And if even this is too complicated for you, I can tell you something more. Yeah. So suppose this here is your body. I mean, the body you are interested in, not your physical body. This thing here. So say this is your body. Yeah. So then, if you are interested in something like the torque, where again you have to integrate over, you can do this the same way, but you have to integrate also with the distance to the body, to the center, or and so on. Yeah, or when you want to have this very instantaneously, then you have to really integrate over the entire boundary. If you just want to know what is the average momentum exchange, then you can even simplify this further, because you could say that this is the wrong. So at the end of the day, you could say that everything that moves into this body has to go through a closed envelope of this body. Yeah. So it is actually sufficient to take a closed envelope of the body and calculate what is going in and out. So this is not temporally accurate because it's not instantaneous, but for an average velocity that would be true. Yeah. So if your body has a complicated shape, and it's not, I mean, there's one thing that makes this potentially difficult. If your body is somewhere attached to the floor and you just want to know the force on the floor, yeah, because then your encapsulation must not include the floor, and this can be difficult if the thing sits on the floor. Yeah, but if you have a free floating body, then all that you need to do is to put an envelope somewhere around it and calculate what is going into and out of this envelope, and this gives you the force that is acting on the body. Okay, so that's basically it with regard to this. Any question with this? Because then, if not, I will ask my typical question. Do you want an exercise? Okay, I have nothing let's say I have nothing really prepared, but there's one thing that we could and should do. So what we reasonably would do now is to implement a cumulant kernel, right? So I told you that in this lecture we have not yet discussed on how this is practically done in reality, but we can still why does it look like there's a problem with this? So it's saved. Okay, I don't know. Okay, so I told you computing cumulants can be pretty difficult, in particular in 3 dimensions. Now this is a 2-dimensional code there, it's not such a big deal. Yeah. What we are going to do then is we'll take this, I hope I'm not completely messing up now without having anything prepared. So we'll take our we'll take this kernel for MRT, which I know I have not uploaded. You may have noticed this. You can get everything out of the YouTube. Just watch it and type. So let's say we'll call this. I was told I should not call it cum. Yeah, I should call it cumulant. Okay, we'll call this cumulant and we'll add we add it here. Okay, so challenge for all of us. Now we have run cumulant, and so I'm not bothering now with the question whether we do this in an efficient or inefficient way. It's just, okay, we'll try to get it done, yeah? And I have an appointment later that will run into the night, so I don't have infinite time now. So let's just get something done. So I told you that usually it is easiest to use central moments, but then we have to go through two transformations. So let's potentially try out to use just one transformation and being aware that this may not be optimal. Now, what is not optimal is that I cannot go to my taskbar, and without my taskbar, I will not be able to look into Mathematica, because this is now what we need. Mathematica is not working, so I'll have to kill it. Okay, let's just kill it. So let's have Mathematica on. Boom, boom, boom. Sorry. Did you notice that computers become slower and slower every year? I mean, this will become much, much worse when everybody is only using artificial intelligence. Nothing normal running anymore. So let me see. Make it large enough so that we can actually see something. So now how do we get, now let's try to bring this to a practical use. What we learned with the chain rule, and fortunately Mathematica is doing this for us. Yeah. So let's look at this. So say we have we take the derivative of x of f with, and f is a function of x and y. Actually, this would now be velocity, frequency things, but this is not x, y, but I don't want to write these strange letters here now. So we'll take now the derivatives. So say we want to know what is the moment. So what's okay? So now this is how we would get to the moments. Yeah, but if we want to have we want to compute the cumulants, yeah, we'll have the logarithm of this. So now you see we get out this guy here, which basically means this is the first derivative of f. Yeah, and if we evaluate this at x and y equals to 0, so this here will become rho and this will become velocity. Yeah. So, and this is what I'm going to tell it, namely that this here is okay, I do it a little bit differently. So because I'm a little bit concerned that it's replacing it too fast. So what I can do to avoid this is to let it evaluate this and then using the result in the next line. Yeah. And in order not to see everything twice, I put a semicolon here. So, okay, I'll tell this that this here is rho. Now, when we later want to okay, you know, I do something else. I'll just, not to confuse these things, I'll call this x, x, and y, y, right? Okay, no, I do it the right. Oops, that was wrong. So let's do it the right way. Yeah. So Xi, yeah. President Xi doesn't like this letter, I know. Xi and upsilon, so that you actually see how it's supposed to be written. Yeah, so this is how it's supposed to be written. So, and then say this is Xi, so that would be the first one, and say that Xi upsilon, so because I don't want to mess things up. Later, if you look in our code, I tell you why we do this. So the 0 moment comes as rho xy, right? So I want to replace this by rho xy. So because I want to, my God. So, and okay, it's complaining here that it don't want to replace it, but it does it anyway. Yeah. So I now don't care about its complaining. Yeah. So this is rho, and this here is supposed to be u, which again is in x and y times. Now this is important. This is actually u times rho. So it complains again, but you see we get out the velocity. So I don't know how to turn off this complaint, but let's just deal with the complaint, yeah? So you just see that I'm not prepared, yeah? So so that would be V. So I mean this of course looks different, but the idea now is that we can put this to C form. And this gives us the right form of this. So that means, so for example, if I want to see something else, so for example, a second derivative of this, which for example, if I don't want to write the same letter again, I can do this also this way. No, I cannot. Oh, I can. Yes. Okay, I know. Okay, let's forget about the C. Okay, so stupid. So now, right. So what also we have to do is we have to define all the other moments. Let's have a look how we did this. So the other moments are local variables and they are just M20 stuff, right? So what's so we have to we only have 9 moments, so we'll do this by hand. So we'll have this here replaced by M20, then this here replaced by M02, then we have, so by these here are the derivatives, right? This is how Mathematica writes this derivatives. We replace this by M11. So now we have all the seconds. Then we want to have third moments. M21 and 1, 1, 2. M12. And then we have only just 2, 2. Okay, did I forget anything? M22. So it's complaining, but it gives this result. Okay, there's one annoyance here. This annoyance is that if we put this into C form, was this written C form? Yes. So if we put this into C form, it puts this power here. Yeah. So okay, I'll do another update in between here. So what I can do is to replace. So I guess that, okay, so the trick is we take anything which we indicate by this plank that comes to a square and replace this by a times a. Now, unfortunately, it would immediately write this as a square, but we can prevent this by hold form. I think we've already done this in the previous lecture, yeah? So, hold form. So, now if we do this, it comes out, so it does not come out. So the reason why it did not come out is because I was not indicating this. And in order not to be confused, I put a semicolon here so that they don't get output. So now if I do this, I get exactly the transformation from the moments from, so I see the moment, the second moment in C has the second cumulant has this form. Yeah. So, and maybe if I make the screen a little wider, I may be lucky and it will also write it in a single line. So this is what I can use for the transformation. Now, okay, so now there is one thing, since I'm a little lazy today. We made one observation. And the observation that we made is that these second order moments, they were already Galilean invariant. Yeah. So if we want to save some time now, we could make the point to say that we leave the second order moments up to here in the format that they are, and we relax them like this. So we do a little bit of hybrid here, yeah, and only care about the ones that are different. And the ones that are different would be the two third order moments and the fourth order moment, yeah. So we'll leave it at that. So we just look at, so we don't care about this, but we care about now this is a third moment. Okay, so right, there is okay, one important observation. We see here what comes out is M21 divided by rho. That's because the cumulant is always a intensive quantity. Yeah. Now this rho, you see, we divide everything by rho, and rho is a conserved quantity, so it doesn't matter. So it is kind of more convenient to not do this division and then later multiply it again. Yeah. So let's not relax the cumulants, but the cumulants times rho, right? So let's just say we multiply these things here we multiply what we're computing here by rho. So rho times this. So now, okay, now I should potentially, I'll put a full simplify here in order to get it a little bit, more convenient, easier format. So because we were now using the raw moments, what we get out is a little longer, yeah? But suppose we don't care, we assume this is correct and we just copy and paste this. So let's just copy this. And now there is one important thing. We want to compute these third order moments cumulants okay, we are not using cumulants, but we are using cumulants times rho, right? So, and we want to have the incoming population moments, so all of them now need not to be modified at this point. So we go directly after we have the moment transform. And in here we'll define a float C2, 1. So this is now my cumulant times rho. And I copy into this my outcome. So now this is here the transform to this cumulant, yeah? And it's already in the format that we need because Mathematica was helping us with this, even though it was complaining because we are trying to address something that it cannot resolve. Okay, sometimes we have to live with complaint, yeah? I mean, I also sometimes have to live with complaint from my students and from my... Okay, let's see the other one. The other one. We are here. So float C12 is equal to that guy. When you take out things from Mathematica, they are not in a nice format. So is all of this plausible? Well, yeah, so velocity, this could be true, right? Okay, I don't get used to this. So now we have only one left, and this is the first order one. Why on earth didn't this, why didn't this work? I mean, it actually looks I have the impression okay, it actually looks better expanded for whatever reason, I don't care, yeah? So, no, it does not. Why does it? Okay, let's. Okay, we are not going to spend a lot of time with this. So what I'm going to one thing annoys, no, I need one thing really annoys me. So just different forms. So what I would like to is I want to have this, I'll tell you later why I want to have this in front, yeah? So what we see here is we have here power left. We'll deal with this here. So we say there's a float C22, yeah? And now we'll add this ugly stuff. Let me kind of trying to get this a little bit better organized. And I'll stop organizing here and okay, I mean, we can deal with this very easily. So you see, it's ugly, and this is only 2 dimensions. In 3 dimensions, it's much more ugly. Okay, I'll put semicolon here and then it's a three-liner. So the thing here, there's this power that we don't like. But this is not a problem. All we do is we write this out directly. Yeah. So that's all we need to do. Okay, now we've done these transformations. Now we go, so the ones that we don't have are these. So we just do this replacement here. We're using the same relaxation rates. Now, what's about the equilibria? What you learned about cumulant? There is no, so the equilibrium is 0. So delete the equilibrium, right? Ah, okay. Of course, this way. So now you see we leave the other three, we leave them in terms of their raw moments. So and now we after this, so of course we have to do the back transform from the pressure, the trace to these actually raw moments, and now we have everything here back in updated raw moments. Yeah, so now they are post-collision states. Now what I'm missing are these three in post-collision states. So how do we get them? So I suggest to do the following. I will, okay, in order not to make a mistake, I will put a plus here and put a bracket around everything. I hope you agree that this should be the right thing to do. Yeah? Right? I mean, this is possible. Yeah? I just want to have this moment separated from all of the rest. Yeah? So, and here I do the same thing. Now the others had a minus here. There's a, I'm not completely sure. I think that Z would allow to do this, but I'll do it another way. I put the bracket around here. So I've not changed anything with this. So what I want to do is I want to go back to these moments after I've computed updated all of these parts. So what I'm going to do is I'm taking these things here. Oops, why is this so long? I'm taking these things down. So I have to make sure that everything is updated and everything is written back. So also these guys here, yeah? So this is just before we do the push. So here I get Cumulant's 2 moments. So copying them back. Looks ugly. So of course no float here, yeah? So this is not a declaration. So in order to turn this around, I want to write M, 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 and I want to write C, C, C. And now the reason why I put the bracket around all of this is because I just put this on the other side. Okay? Agree? So then I have my moments back. So now I should save this. And still we have this compile. Okay, so this doesn't work because we are not in the right folder. To go to LBM. CD, what is this? We are in no, these are unfortunately, this is last year's at the LBM 20, right? So here's the right thing. So now we are bashing the
There's a typo in the function name.
typo in the function name. Where?
The run cumulants.
Run cumulant is a typo in the function name. You mean this one?
Yeah.
Did I do it correctly down here?
Yes.
Okay. So save again. Thank you. Compile. Bash compile. I mean, it's not getting faster the more functions we add, yeah? What was this thing? Run simple. I think this is the one that we were using for running. Is there anything? So okay, we'll have to wait until it compiles. Usually, if there's a mistake, so we have to restart again. So last time we ran this. Okay, I was not sure why we had this. Unindented does not match. Okay. What have I done? So apparently, so this happens only in Python. Okay, now this is running the MRT, yeah. So this is actually not what we want to see. So I interrupt this. So we have not basically we should restart. I mean, I wanted to restart it anyway, yeah, so restart it. So now try the same thing, try out the same thing with cumulants. Okay, so it's not visible that it is necessarily better now so far. Yeah, so there is this. I don't know where this oscillation up there is coming from. So maybe we have some problem with the boundary conditions. Yeah. So then unfortunately, I mean it's not. There is a method to limit the range. I've forgotten how to do this. Do you have enough? So usually I would now ask ChatGPT to limit the range. Okay, should we do this? Because okay, I'll just use autopilot and now this is on the recording, yeah. How to set the does it know what I was? I think there's too little context. I was not implying what I. Okay, V-min, yes. V-min and V-max. Maybe that's already enough. So V-min is equal to 0, and the other one V-max is equal to should be 0.1. What have I done? I think I should do this. What did we set as a velocity? By the way, 0.08. So already we should not go further than that. So let me interrupt and run. So okay, here's the maximum now. There is some boundary fluctuation which does not cause any instabilities or stuff. Now we unfortunately have not yet seen any difference with regard to what. Okay, let's, I don't know, do this a little further. Interrupt, run all. And the problem with low viscosity is that it takes longer, yeah, because it takes longer for stuff to get into the domain. I think that the boundary condition is here really a concern, and this is a little bit unfortunate because the boundary condition is in common for both methods, and so we may not be able to appreciate what difference this could have made. So this is going to be a little bit too ugly here. I think we should actually go to back to a smaller viscosity, a larger viscosity, and maybe. So I think this is the. I don't know. Try to kill it. So we observe some oscillations. We actually killed it.
The max of velocity is.
Yeah, it's too low now. I know. So now we actually killed it because it was too. I mean, we always. I think we need to restart it because otherwise it will restart from the Did we use delay or no delay here? Use delay everywhere, right? Yeah. I'm actually wondering whether we did this corners correctly. Yeah, there could be a problem. There could be a problem here. Okay, so I mean maybe let me see, what is it here. We have now not done a comparison between MRT and Cumulant, but I think that we've seen that the Cumulant version also works with this to the same extent that the MRT method worked here. Yeah, so maybe you can yourself try it out and see some differences or things in common. Yeah, so this is going to crash it now. I mean, one thing that we could try, and this would now be very annoying, is now we've seen that the Cumulants die. And maybe the MRT does not die. So if this now happens, we'll stop and be unhappy for today. But this can also be the case. So I mean, also we are not completely confident that we didn't make any mistakes in all of this. But this also looks like something that won't survive forever. Okay. So we have a problem with this singularity. There is a limit to everything. Yeah. We now have a high velocity. We also have a low viscosity, and we may not have completely correct boundary conditions up there. Anyway, it's on the recording. It was was just. I think it looks like this lives longer. But yeah, okay, may happen. It looks nice. Really interesting. So it's your homework to find out what is the difference. Okay, see you next week. Yeah.